Hi, I'm Dara Singh, and I'll be presenting work with Anna Shapiro and Ken Norman on a neural network model of memory consolidation during sleep. Systems consolidation theories, such as the complementary learning systems framework, have posited that the hippocampus supports the rapid learning of new information and then somehow helps neocortical areas to consolidate this information during sleep. As these theories predict and as Kitamura et al. Show, while episodic memories create cortical traces, these are not well developed enough to support memory behavior. Over time, however, and with hippocampal support, cortical traces mature and can support memory independently. In this work, we ask, how does hippocampus teach new information to cortex? Our first simulation provides an account of how slow-wave sleep could support consolidation in a category learning task. In the experiment we simulated, humans were required to learn novel satellite objects belonging to three different categories. Exemplars contain some features that were shared with other members of the category, as well as features that were unique to each exemplar. Participants learned these satellites either at night and were tested again after a night of sleep, or in the morning and were tested again after a day awake. Participants in the sleep group showed an improvement in memory for shared features, suggesting better understanding of the category structure with sleep, as well as a preservation of memory for unique features. Our model architecture consists of two major components. First, we have Seahorse, a fast learning model of the hippocampus, which instantiates many biological properties of the hippocampal subfield circuitry. Second, we have a slow learning cortical layer representing the ATL as a target of consolidation. Our simulation protocol consists of first training the model directly on the satellites analogously to human awake learning. We then allow the model to go into a slow wave sleep phase where it will autonomously replay the satellites and help the ATL develop useful representations of these stimuli. So how does the model learn over sleep and support cortical consolidation? We initiate sleep with a random noise injection, after which all external input is silenced. The model then autonomously reinstates item attractors. Each sleep trial is governed by the overall stability of the model's activity. Here I have a schematic of a replay event on the left and the stability time course of an event on the right. As the model first falls into an attractor, its activity is highly stable, and this marks the plus phase of the event. Short-term synaptic repression gradually destabilizes the attractor. The stability drop causes the plus phase to end and the minus phase begins. The model has oscillatory activity. During the minus phase, as the attractor distorts, two useful contrastive states are revealed by the oscillations. First, when inhibition is high, the weakest synapses that are part of the attractor have reduced coactivation. Second, when inhibition is low, synapses that are part of neighboring attractors have increased coactivation. As the attractor is further destabilized, the minus phase ends, and the model traverses to the next attractor. Weight changes occur in the model at the end of each minus phase by subtracting the average minus phase coactivations from the average plus phase coactivations. This allows the model to both strengthen weak parts of attractors and weaken interfering parts of neighboring attractors. What does sleep replay look like? Here I have a chord plot showing transitions between 15 satellites. We find that individual exemplars transition to exemplars of other categories at the same rate as they do those from their own categories. We expect that this uniform interleaved replay should support effective learning of category structure. So how does performance change over sleep based on this replay? This bar plot represents pre versus post-sleep test performance for shared and unique features. We turn hippocampal learning off during sleep, so this performance changes based on learning in the ATL. We find substantial improvement for shared features as in the human data, indicating successful autonomous systems consolidation that may provide an account of the processing occurring in the sleeping human brain. However, a problem arises. How does cortex integrate new information without catastrophic interference with its existing representations? Often, an environment is non-stationary, and somehow we must protect existing cortical knowledge without external refreshers. We propose in this model that interleaving slow wave and REM blocks over a night of sleep allows cortex to learn new information from hippocampus during slow wave sleep and preserve its existing cortical knowledge during REM. We employ an AB-AC list learning task for this simulation. First, we train the AB list on an ATL-only network. This simulates previously learned knowledge of the cortex. We then train the whole network on a new AC list, which has overlaps with the AB list. Given that hippocampus learns faster than cortex, it primarily supports AC performance. The model then performs slow wave and REM sleep interleaved. So how does this allow for consolidation of new information and protection of old knowledge? Here I compare two conditions. In the first, slow wave and REM sleep are interleaved for 5 epochs. In the second, there are 5 epochs of slow wave sleep exclusively. On this panel is the time course of AB error increase corresponding to interference for old knowledge. There is a significant reduction in AB damage when slow wave and REM sleep are interleaved versus when there is only slow wave sleep. On the right, I show AC error decrease corresponding to consolidation of new information. There is no difference in AC error reduction between the two conditions. The results from our simulations together provide an account of how the hippocampus teaches cortex new information, as well as how cortex is able to preserve its existing knowledge structures. Thank you. Please get in touch with any questions. If you're interested, please also visit our session.